All right, friends and neighbors, welcome back to another networking video. I think this time we're going to take a little less technical approach and we're going to do a little history. So maybe we'll do a little story time this time. And so we're getting ready to do a border gateway protocol series, right? So we'll get through all the technicals and we'll do a build and so on and so forth. But BGP brings up this idea of an autonomous system. And so since this is really the first time that this appears, other than when we were talking about OSPF and some of the other videos, I thought it might be good to understand where in the world that came from and what it really sort of means. So without further ado, Border Gateway Protocol in the beginning. So the organization or the agency behind all of this is the Defense Advanced Research Projects Agency, or DARPA, not to be confused with the Dharma Initiative for fans of the TV program Lost. And so right from the DARPA site, we have, for 60 years, DARPA has held to a singular and enduring mission to make pivotal investments in breakthrough technologies for national security. So ARPANET came out of DARPA, right? So the genesis or the provenance of the internet as we know it today came out of a couple of research networks. The fun statement from DARPA is the genesis of that mission and of DARPA itself dates to the launch of Sputnik back in 1957. And in a commitment by the United States that, from this time forward, it would be the initiator and not be the victim of strategic technological surprises. So, stay on top of advancements, stay on top of science so that you're not surprised. And so that's sort of an interesting statement. And among all of the other projects that they've done, ARPANET was one of them. So ARPANET and then its sort of successor, the NSFNET, both got its start, decades ago. So in 1969, the precursor to the internet began with the U.S. Defense Department's, right, Defense Advanced Research Projects Agency, ARPANET. And so the ARPA-funded researchers developed many of the protocols still used for most internet communication. I'm going to show you something later that'll sort of blow your mind, but it's good to realize that that's an important statement. So a lot of this dates from that fabulous decade, the 1980s. Whatever TV program, whatever your hairdo, and whatever you were wearing, the 1980s were really, really big for internet technological advancements. Now, we sort of have to remember that at this time, things were growing, right? More and more universities, more and more research centers were trying to connect to each other. And right above me there, you can see a very early diagram of ARPANET. And that's right from that PDF right there that I've cited. So you can go out and take a look at the history for yourself. It's actually quite interesting to take a look at both the history of ARPANET and NSFNET. So how to provide greater access to the high-end computing resources. So that's sort of the goal. And of course, any solution that was going to be implemented had to connect all of the universities. And from that same document, we have this really nice sort of timeline that shows the evolution of ARPANET. And so ARPANET started in the late 60s, early 70s, and went all the way through to the 80s when it was eventually replaced by NSFNET. So this is a really nice graphic that sort of shows the growth. And you can see the sort of initial diagram that we see down here, right? This one. And then all the way through the addition. Now, we could talk about things like the network access point structure, but we don't even have the internet as we know it until the early 1990s when we have things like the very first browsers coming out. So, or the very first graphical browsers, I should say. So that is after all of this is done, right? Way out here at the end of that timeline. So that's sort of interesting to realize. Now, just for fun, one of the first cellular telephony deployments was also in the early 1980s in Chicago. So the NSFNet, as you saw that ARPANET was spinning down in the late 1980s, and so NSFNet went online in 1986. And this is kind of crazy. The first connectivity level was 56K, which of course is the speed of the super fast dial-up modems. Well, of course, today we have high-speed internet, so that sort of goes by the wayside. But the entire structure, the backbone structure, was 56K. And then, of course, later it was updated or upgraded to T1s and then to T3s. But even T3s are only 44 meg. And this is one example of the growth. And we could see lots of universities and supercomputing centers. Now, at the heart of all of this, of course, is the organization BBN. So if you want to have a little fun with history, take a look at BBN. Now, the previous statement, ARPA-funded researchers developed many of the protocols still used for most internet communication. That couldn't be more true. If you take a look at all of the protocols that sort of form the basis of our transmissions, they include IPv4, Address Resolution Protocol or ARP, Transmission Control Protocol, TCP, User Datagram Protocol, UDP, Internet Control Message Protocol, ICMP, just to name sort of the big five maybe. But all of these date from those mid-1980s. In fact, all of them have RFC numbers that are below 1,000. And so while these have had additions, they certainly haven't been replaced. So for example, IPv4 is exactly the same format that we used in the beginning. Now, the DSCP field replaces the type of service field, for example. Certainly, the transmission control protocol has been modified and updated. As an example, we have sliding window scaling as opposed to the original 65K sliding window. And all of that stuff was collected together in RFC 9293. But UDP, almost exactly the same. ICMP, almost exactly the same. Address Resolution Protocol, one of the simplest protocols you'll ever study, pretty much the same. So why in the world would we, in a BGP video, take a look at all of this history? Well, what we're trying to convey here is that we've got internet growth, and we have more and more centers trying to communicate with each other. And so internally, they have their own networks, but then how do you get networks to talk to each other over a wide area? So in the beginning of all of this, there were a very small number of what we might call routing protocols. There was the gateway to gateway protocol, GGP, and something called the exterior gateway protocol, EGP. Now, a couple of notable documents, if you want to read a little bit more about, sometimes it's fun to look at history from sheer, oh, look at all this cool stuff that happened and look at the people that were involved. But in many of these documents, the discussion as to why decisions were made or problems that existed are part of the early documents, and they're not part of the later ones. So that's one of the reasons I like to go back to these things. And of course, if you've looked at any of the videos on this channel, you know that I really, really dig standards and RFCs because these represent the specifications that everybody's supposed to adhere to allow interconnectivity. So IEN 30 gateway routing was all about a particular way for gateways to communicate with each other. And then, of course, after this, right, 1988, we get things like the Routing Information Protocol, which was based on something called Routed with the Berkeley distribution software, the Berkeley software distribution. So internally, everybody can have their own structure, but how do you connect, say, one university to another one? Now look at the date for RFC 827, 1982. That is the exterior routing protocol, and that is what gets us to where we are now. So growth, connecting all of these sites, and then how do you get one site to talk to each other? And so here's a couple of quotes from RFC 827. It is proposed to establish a standard for gateway-to-gateway procedures that allow gateways to be mutually suspicious, right? I'm not going to accept things from you just because you're advertising them. The issue is, right, it's expected to be a continuously expanding system. That is the early ARPANET, with more and more hosts and more networks participating. Of course, this requires more and more gateways. So if you think about that for a sec, all of the organizations and all of the universities and all of the companies that are connected to the internet today connect to the internet through a gateway. And so Each one of those today, of course, has many, many, many networks on top of that. So in the future, the internet is expected to evolve into a set of separate domains or autonomous systems. This is where we see the language beginning, each of which consists of one or more relatively homogeneous gateways, meaning that if you look at the requirements for internet hosts and you look at the requirements for IPv4, those gateways are supposed to adhere to that. They're supposed to support a certain number of features and header construction. And so that is the motivation for all of this. Okay, we all want to do IPv4. We all want to connect to each other in the same way. We might have individual ways of doing things internally, but let's figure out a way that we can all communicate in very similar fashion, at least between these separate domains or autonomous systems. There it is. So RFC 904 comes in. Now it's an update to the Exterior Gateway Routing Protocol. EGP exists in order to convey net reachability information between neighboring gateways, possibly in different autonomous systems. Now, this also means that if you've got a gateway, you might have one network behind it, but you might have lots and lots of networks behind it. So if your neighbor wants to be able to get to all of your networks, or if you want to allow neighbors to get to all of those networks, you might be advertising multiple networks to your neighbors, not just one. So you might have a fairly complex internal structure. So the protocol includes mechanisms to acquire neighbors, monitor neighbor reachability. All right, can I still talk to my neighbor? Exchange net reachability, right? These are the networks that I have behind my gateway. What do you have behind your gateway? So we've got update messages. Now, if you've looked at routing protocols before, you know that routers exchange data with directly connected neighbors. Now, they have lots and lots of different ways to do that, lots of different algorithms behind the messaging, algorithm behind the protocol. But this is a way to exchange network reachability information between neighbors on a much larger scale. So the protocol is based on periodic polling. Okay. Hello messages. Okay. And then you can also ask for updates. Here's mine. By the way, could you tell me what you've got going on? Well, that's very nice. That's terrific. But what about BGP, right? So far we've talked about EGP. Where does BGP come into the picture? Not until 1105. So in 1989, this is the first time that we see BGP used. And the whole point of BGP, right? BGP, or the Border Gateway Protocol, is an inter-autonomous system routing protocol. How about that? It is built on experience gained with EGP. Oh, so this whole thing with EGP was getting us to BGP, and BGP is updated, performance characteristics changes, additions, and modifications based on the experience from the previous exterior gateway protocol. So all of these RFCs, 904, 1092, and 1093, were sort of informing the BGP RFC 1105. So at the time of the writing, the Border Gateway Protocol implementations exist for Cisco routers. How about that? So Cisco was in on the game very early on, as well as what was called the NSFNET nodal switching systems. And a public domain version for gated is currently being implemented. So this is where we were in the late 80s, right? So this is the Border Gateway Protocol. Now the fun part about this is that this is a relatively early version of Border Gateway Protocol, but fast forward 30 or 35 years, we're still using BGP, although a different version. So the whole purpose of BGP, primary function of a BGP speaking system, is to exchange network reachability information with other BGP systems. So you've got your autonomous system, I've got my autonomous system. Within my autonomous system, I have these networks that I'm willing to allow public access to. You've got a certain number of public or publicly available networks, and you're going to advertise those. But even more, I might reach another AS through you. And so the BGP system gets more and more complex, but adds more and more reachability information. So The network reachability information includes information on the autonomous systems that traffic must transit to reach these networks. Here we go. This information is sufficient to construct a graph of AS connectivity from which routing loops may be pruned and policy decisions at the AS level may be enforced. Okay, when you think about networks as a graph, and most forwarding decisions do just that. So you can build a layer 2 network connectivity graph and then implement something like span and tree on it to enforce a tree-like structure on your layer 2 graph. But we certainly draw layer 3 connectivity. In fact, the OSPF RFC is filled with ASCII art depicting graph structures where the routers are the vertices and the networks are the edges. And now this is going to be a network of ASs. So if we move beyond routers and edges as networks and say, oh, let's draw a graph of AS connectivity, and only when we zoom way in to an AS do we actually see the host network, the host AS networks inside there. We've got a whole other layer of graph connectivity. Kind of crazy. All right, well, I think that's enough for now. So BGP's roots go way, way back. And so as the internet was expanding and more folks were connecting, more and more gateways were connecting, more and more networks behind those gateways, it was envisioned that the internet would actually be a collection not of just networks and routers, but rather of organizations or autonomous systems connected together, separate administrative entities. And BGP's point and purpose was to advertise network reachability behind or based on AS numbers, but also the ASs that you might transit to get to other AS connected networks. So lots of history, lots and lots of very hardworking people. That's another reason to look at the history, I think, is to realize that there were an awful lot of people that were, I mean, in on the ground floor and reading about this. We sometimes hear about the famous folks like Vint Cerf, but there were lots and lots of other folks involved in this. Okay. Well, thanks for watching. Thanks for listening, even though this might have been a history lesson or a little bit of story time. Like and subscribe if you enjoyed the journey start, and may those packets always reach their destinations no matter how many ASs you have to go through.